Welcome to this concept explainer brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today we are taking a deep dive into Unit 4, Moving Charges and Magnetism. We'll be focusing specifically on the force between two parallel currents and, more importantly, how this force actually helps us define the ampere itself. Our goal is to make this simple, clear, and absolutely exam safe for you. Now, before we get into the heavy mathematics and the definitions you need for the exam, let's start with a simple question. We know that any wire with a current creates a magnetic field around it, right?
Yes, of course. That's the basic idea from Ørsted's discovery.
Exactly. So just imagine two very long, thick power lines. They're running parallel to each other, both carrying a huge amount of current. Do they just sit there, or do they feel some kind of invisible magnetic push or pull between them?
That's an interesting thought. I mean, since they both have current, they're both basically electromagnets, so I suppose they must interact. My first guess, and I think a lot of students would think this way, comes from electrostatics, like charges repel. So maybe they repel each other.
That is a very good intuition, and it's precisely where physics gets surprising. The wires absolutely feel a force, but the direction is quite counterintuitive, and it's critical for engineering. Think about high-voltage transmission lines. They often carry currents in opposite directions. We call that antiparallel. The repulsive magnetic forces between them can be so enormous that engineers have to use extremely strong insulators and support structures
Just to keep them apart.
just to prevent the wires from whipping apart or vibrating because of this hidden magnetic push. This force is not trivial at all. It needs serious engineering, and it's the key to defining the most fundamental unit of current we use every day, the ampere. Okay, let's unpack this. The core idea is actually quite simple. It's a two-step process. First, wire 1 creates a magnetic field. And second, wire 2, which is sitting in that field, experiences a force. It's that simple. And of course, this works both ways, which is consistent with Newton's third law. If wire A pulls B, then B must pull A.
So it's not a direct interaction, but one wire's field acting on the other wire's current.
Precisely. Now for the fascinating part, the direction. You have to forget static charges for a moment. In magnetism, we find that parallel currents attract and antiparallel currents repel.
Okay, that's the opposite of what I thought. Like currents attract. Why does that happen?
It's all about the geometry of the field. So let's use an analogy. Imagine two swimmers in a river swimming side by side. So they're parallel.
Right.
As they swim, they create disturbances in the water. If they swim in the same direction, the waves they create in the space between them actually pull them together. It creates sort of low-pressure area that sucks them closer. That's our magnetic attraction.
So the magnetic interaction is the opposite of the electrostatic rule. Like charges repel, but like currents attract.
Yes, and we can prove it with the right-hand rule. Imagine current is flowing upwards in both wires. So they are parallel.
Okay, both up.
The magnetic field from wire 1 circles around it, clockwise. So in the region between the wires, which way is that field from wire 1 pointing?
It would be pointing into the page.
Perfect. Now, use the other rule for the force on wire 2. Your fingers point up with the current, your palm faces into the page with the field. And where does your thumb point?
Ooh, it points to the left, towards wire 1, so it's an attraction. I see it now.
Bingo! That's the proof. The fields interact in a way that creates a pressure difference, squeezing the wires together. This is the very phenomenon that Ampere studied between 1820 and 1825, and it forms the entire foundation of how we measure current. Now let us see how insert defines this, because this definition is probably the most common 3-mark question from this section. It's so important that it actually defines the ampere, one of the 7 SI base units. Could you please read the exact definition for us?
Of course, it says. The ampere is the value of that steady current, which, when maintained in each of the two very long, straight, parallel conductors of negligible cross-section and placed 1 meter apart in vacuum, would produce on each of these conductors a force equal to 2 by 10 certains per meter of length.
Excellent. That is the exact wording we need for the exam. Let's briefly look at the logic behind the force calculation. It's a really neat 4-step process. First, we calculate the magnetic field, B1, that's produced by the first wire. We use Ampere's circuital law for that.
Right, which gives us B equals mu naught I over 2 pi d.
Correct. Then, step 2, we treat the second wire as just a conductor sitting in that external field, B1. Step 3, we calculate the force on that second wire using the Lorentz force extension. F equals I2L cross B1. And finally, we just substitute the expression for B1 into that force equation.
And that gives us the final formula for the force per unit length.
Yes, exactly. And that formula is F by L equals mu naught I1, I2, all divided by 2 pi d. You can see how the force is directly proportional to both currents and inversely proportional to the separation d. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now let's do a quick conceptual calculation. Let's say we have two wires carrying a moderate current, maybe 10 amperes each, and they're separated by about 5 centimeters, so 0.05 meters.
Okay.
If you run those numbers, the resulting force comes out to be 4 into 10 to the minus 4 newtons per meter.
That seems incredibly small. How can such a tiny force be used to define a fundamental unit?
It is small, but it's very precisely measurable, and that's the key. The fact that we can measure the small mechanical force validates the entire definition. It provides a reliable, repeatable standard. So what we've just done is connect two major principles of this unit: Ampere's circuital law to find the field B, and the magnetic Lorentz force to find the force F on the current in that field. It's a perfect application of both. All right, now let's talk about the silent killers. The common mistakes that cause students to lose marks in the CBSE exams. The first killer. Students confuse the relationship between force and distance. They often think it's an inverse square law, like with charges.
Because of Coulomb's law.
Exactly. But for these long parallel wires, the field goes as 1 by d. So the force also goes as F is proportional to 1 by d. If you double the distance, you just halve the force, not quarter it.
Okay, so I must remember it's a linear inverse relationship, not inverse square.
Precisely. Now the second killer, and this is the big one, it's the ultimate trap. Because in electrostatics, like charges repel, students just assume parallel currents must repel. This is completely wrong.
Right, that was my initial thought too. So I must remember that when the charges are flowing in the same direction, the wires actually pull each other closer. The logic of static charges must be completely dropped here.
Precisely. If you can drop that old electrostatic logic, you save yourself those crucial marks. Now, to make sure this stays locked in your memory forever, let's use some memory anchors. First, a simple mnemonic. Just remember this phrase: PI attracts, ANT repels.
PR for parallel, ANT for anti-parallel.
Exactly. Say it 10 times if you have to. PAR attracts, ANT repels. Next, use a physical gesture. Use your right hand. Your fingers are the current, your palm faces the direction of the magnetic field. Your thumb gives you the force. If you actually do this for parallel currents, you will find your thumb always points towards the other wire. It forces you to see the attraction.
That's a great idea, to physically check it every time.
And finally, think of our two swimmers again. Swimming together, parallel, they glide easily and get pulled together. If they try to swim against each other, anti-parallel, the turbulence just pushes them apart. Okay, so let's close this deep dive with the 3 most important exam safe points. Number 1, the force per unit length between two parallel wires is given by F by L equals mu naught I1 I2 over 2 pi d. The force is proportional to the currents and inversely proportional to the separation. Number 2, the fundamental rule of interaction. You must remember that parallel currents attract and anti-parallel currents repel. This is the opposite of electric charges. And number 3, this very magnetic force is what defines the ampere. It's the current that produces a force of exactly 2 into 10 to the minus 7 newtons per meter between two conductors 1 meter apart in a vacuum. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROFSam, right?
Yes, ProfSam.com. Thank you for joining us for this deep dive. Go and conquer your exams.